Okay, so in section 12.8, we are talking about how cylindrical and spherical coordinates, which you learned back in section 9.7, how these coordinate systems can be helpful in computing triple integrals. So let us look at a few things here in the book, and then we'll get to some examples. So let me just see here. Yeah. So this is the volume element, okay, in cylindrical coordinates, the volume element. So remember, every one of these triple integrals, you have a dv involved, right? So for instance, in rectangular coordinates, dv was equal to dz dy dx, or dz dx dy, or dy dx dz. You know, you had 6 different orders there. For a cylindrical coordinates, for a volume, an element of volume in cylindrical coordinates, dv is equal to r dz dr d theta. So you see, if you wanted a volume of a little block of volume, you would multiply, well, you know, space times width times height, or length times width times height. So in this case, the length is essentially dr, the width is r d theta, which is the area of that, the length of that arc there, and dz is the height. So hence r dz dr d theta. Hold on here. This would be how you would set up a triple integral with respect to cylindrical coordinates. The x and the y, the z stays the same, but the x and the y get replaced with r cosine theta and r sine theta. Okay, and we'll look at an example. Matter of fact, let's look at an example right now. Let's see here. Yeah, this one will do. Let me bring it up here. Okay. Let me give you a moment to copy this example down. Okay, so this problem, we are integrating with respect to rectangular coordinates. And we're integrating with respect to y, z first, y second, and x third. So in regards to the section 12.7, the way this triple integral is written, they're treating the solid region E. Okay, they all call that solid region, or they call it, I like to call it the solid. They're treating the solid as a, hold on here, one moment. Well, they're treating it as a type 1 region, type 1 solid region. And then the projection of that solid region, that onto the XY plane, the region D, would be a type 1 plane region. Okay? So what's going to make this triple integral difficult? What's going to make the triple integral difficult to work out? It's going to be difficult to integrate this triple integral with respect to rectangular coordinates. Why? That's right, Ellie, the square roots, the square roots. Okay, so, I mean, I'm not saying it's impossible, but that square root of x squared plus y squared, I mean, you know, that can be difficult to work with. But let me ask you, can we figure out what this solid looks like based on the limits? I mean, let me ask you this. So we're integrating with respect to z first, right? So that means that your z limits are going to involve a bottom surface and a top surface. Okay, so the solid is bounded above and below by a top surface and a bottom surface. Now they don't say, you know, z equals square root of x squared plus y squared. They don't say z equals 2, but we know it to be there. So let me ask you, what's the top surface going to be? What's the top surface going to be? What's z equals 2? What is that? That's a plane. Good, Ellie. All right, well, the bottom surface is z equals square root of x squared plus y squared. What's that an equation of? What surface is that? You should know. What is that bottom surface? Well, we know it's a surface, so a circle wouldn't be a surface. Exactly. But let's try this. Hold on. So z equals square root of x squared plus y squared. Oh, we don't know what that is exactly. All right, let me square both sides. Then I get z squared equals x squared plus y squared. What's that an equation of? What kind of surface is z squared equals x squared plus y squared? Think about section 9.6, table 2, I believe. What's that an equation of? Begins with a C. Then comes an O. Then comes an N. I hope you can get it now. Come on, z squared equals x. That's right. It's a cone. That's right. That's right, Ellie. That's right, Juliana. And it's the top part, right? It's the top part. Because we got the plus there. Okay, so this is going to look like, it appears to be a cone. And let's go ahead, but we got to, of course, could it be just half of the cone? Could it be the whole cone? Well, region D consists of these bottom and top functions here. Y equals square root of 4 minus x squared, and y equals negative square root of 4 minus x squared. And then you have your x limits going from -2 to 2. Now, what's that going to be? If we were to focus strictly on the y limits and the x limits, what's that going to be? What region D do the y limits and the x limits make together? Oh, okay, well, let's see. Y equals square root of 4 minus x squared. If y equals, maybe I'll put that in blue. If y equals square root of 4 minus x squared, then y squared equals 4 minus x squared. So x squared plus y squared equals 4, right? What is that? X squared plus y squared equals 4 in 2 dimensions. That's the equation of, well, for 3 dimensions, you know, we had a cone. But when we go then to D, yeah, it's a circle now. Right. Now, I mean, what I mean is this is separate from the cone. This is a circle. Okay, so you see how you can use the limits to recreate the solid. So this solid is going to be a cone coming out from the origin, and then it hits the plane z equals 2. That's going to be the solid that's described by these limits. And you have to get good with this, everybody. This is going to be like a big deal, right, on your exam next Monday. This is going to be a very, very important part of the exam, you know. So you have to kind of make these connections, all right? Like I said, you know, this is now we're getting into probably the hardest part of the course. So you want to be, you know when the next exam is going to be. If you can take off a few days at work, that would be good, right? Or, you know, try to get extra time. Cut back at work. You know what I'm trying to say? Usually, I mean, employers, people, if you have an internship, if you're working a job, if you give your boss, so to speak, advance notice, hey, you know, I got an exam coming up. Could I take a few personal days? Usually, they're good about that. Take advantage of that, okay? Because you know you want to do well, okay? All right, let's keep rolling here. So this is our solid E. So difficult to integrate with respect to rectangular coordinates. So here is the solid, and so but before I can convert this triple integral to a triple integral with respect to cylindrical coordinates, I have to know what it helps, put it this way, it helps to know what the solid looks like. Well, this is the solid right here. Okay, and we talked about it. It's the solid E is a solid formed by having a cone on the bottom and a plane, horizontal plane z equals 2 on the top. And then if you project that cone, or I should say if you project that solid E into the xy plane, it's going to trace out this region D. So in cylindrical coordinates, this would be what that triple integral above, this triple integral with respect to rectangular coordinates is going to then is going to then be this triple integral in cylindrical coordinates. And I think too, class, how many of you have a look at the recordings? How many of you go back into course content, find the recordings, the lecture recordings, and look at those sometimes? How many find that helpful? Good, Kino, excellent. Excellent, Madeline. Noah, wonderful, wonderful, excellent, Juliana. I mean, I'm putting a lot of, drawing a lot of things and stuff. Excellent, Malik. And this is designed to help you. It's designed to help you. Okay, so the cone z equals square root of x squared plus y squared. Okay, this cone here, in terms of cylindrical coordinates, this cone would just be z equals the square root of r squared, right? Because in cylindrical coordinates, r squared is equal to x squared plus y squared. And so that just gives me the square root of r. And so that means then square root of r is the boundary, dz. dz goes from z equals r. Z equals r is the cone, the bottom surface, the cone. And then z equals 2 is the plane on top. Then you have to do integral, you have to do your limits with respect to r and theta. Well, a circle of radius 2, r would go from 0 to 2, and theta would go from 0 to 2 pi. Okay? So let me ask you, between the two integrals here, the two triple integrals, the first triple integral is with respect to rectangular coordinates. The second triple integral is with respect to cylindrical coordinates. Which looks easier to do? Triple integral 1 with respect to rectangular coordinates, or triple integral 2 with respect to cylindrical coordinates? Which looks easier? The second one. Very good, Charles. And so these are the things you have to think about when you're doing these kind of problems. Now, that's right, Juliana. In section 12.8, they tell you, hey, integrate with respect to cylindrical, integrate with respect to dense or spherical coordinates, but later on, they're not going to tell you, you'll have to compute a triple integral, and they're not going to tell you what coordinate system to use. So you have to sometimes recognize, hey, this triple integral could be better, could be easier to do with cylindrical coordinates, for instance, okay? All right, well then let's go ahead and work this out. So the integral, I'm going to do the iteration. I integrate with respect to z first, so that means the r cubed is treated like a constant, because when you integrate with respect to z, you're holding the other variables, r and theta, you treat them like constants. So the antiderivative of r cubed with respect to z is r cubed times z. Then you substitute in the 2 and you substitute in the r, okay, and you're going to get then, well, r cubed times 2 is 2r cubed, and r cubed times r is r to the 4th. And now you have a double integral. And you just work it out, and in the end, you're going to get 16 pi over 15. Okay, I'll let you copy that. Please let me know if you have any questions. All right, are there any questions before we move forward here? Okay. Well, then now let's look at the spherical coordinates. So let me go back to the ebook here. Hold on here. Okay. So the spherical coordinates, let's go forward here. So, of course, these are the definitions of spherical coordinates, x, y, and z. And what does an element of volume look like with respect to spherical coordinates? They prove it here. They prove it. They show in figure 7, they actually go forth and prove what a unit of volume would be in spherical coordinates. In the interest of time, I want to, for now, just go right to the formula. You can look at it. They show it there in section 12.8. But this would be your triple integral. If this would be the form of it if you're going to integrate with respect to spherical coordinates. So of course the function of x, y, and z, x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z equals rho cosine phi. You do that back in section 9.7. That's how x, y, and z are defined. But the unit of volume, or the dV, is going to be rho squared times sine of phi d rho d theta d phi. Or you could say rho squared times sine of phi d rho d phi d theta. That symbol there is you know what those symbols mean. So this is how you would integrate if you're going to use spherical coordinates to compute your triple integral. And sometimes students have difficulty remembering, like how many might have a little trouble remembering the rho squared sine phi d rho d theta d phi? How many might have a little trouble remembering that part, the dV part of the triple integral? Like on an exam, for instance. Okay, and now I understand it, and that's why I let you have access to the. I let you have access to those formulas, so that because any engineer would have access to those formulas. You know, I'm not going to have you miss a problem because you don't. You know what I mean for that reason. All right, Marwan likes that, and Malik likes that. Excellent. Madden likes that. Excellent. All right, well let's look at an example now dealing with this. Spherical coordinates. Let's go back to here. Okay, I'll let you copy this example down. Okay. Okay, so we want to find this volume. In this case, we want to find the volume of the solid that lies above the cone and below this sphere. Now, what key word in here tells you that maybe spherical coordinates should be used? What key word in this problem tells you, hey, let me consider using spherical coordinates? Well, that's right, Ellie, the sphere. That's right, Juliana. Big clue. Okay. Well, now is this sphere here centered at the origin? Is x squared plus y squared plus z squared equals z? Is that sphere centered at the origin? The sphere has a little bit of a complicated equation, right? What's making it complicated? In other words, what I'm saying is if you had x squared plus y squared plus z squared equals 25, that would be a sphere centered at the origin with radius 5, right? But this sphere here is harder to work with. And Juliana's noting that you have a z here. Okay, so we're going to have to bring the z over, right? We have to get this sphere in standard form. So I'm going to have to bring the z over. And what am I going to have to do to figure out the center for this sphere? What process am I going to have to use? Because I know that I got a cone below, the solid, there's a cone below and a sphere above, and that's right, Ellie, completing the square. So first thing we have to do is figure out what this sphere looks like. So we go to the next page. Excellent, excellent. Okay, and so completing the square is something you learn. I'm going to just let you copy down this part. Please let me know if you have any questions. I'll give you a moment to catch up here. Okay, so now what we need to do is I'm drawing a picture of this solid. Now, okay, so the cone on the bottom is, well, I want to, as you know from these problems, it's very important to figure out what the intersection of the surfaces look like. What is the intersection mathematically of this sphere and cone? Okay, and you know the sphere, the way I've drawn the picture, the sphere, I'll say it might be more like this. Okay, it might be. I might not have drawn it completely correct, but you get the general idea. Okay. So, all right, what is the intersection? All right, the intersection clearly is a circle between the cone and the sphere. But in order to determine the limits, we need more information. So what I'm going to do is first, I'm going to say, okay, well, this sphere, the x squared plus y squared plus z squared equals z. X squared plus y squared plus z squared equals rho squared, and z equals rho cosine phi. So I can represent this sphere in cylindrical coordinates And this sphere is the sphere centered at 0, 0, a half. I can represent that sphere in spherical coordinates by the equation rho equals cosine phi. Now the cone is z equals square root of x squared plus y squared. Okay, how am I going to represent that? How am I going to represent the equation of the cone in spherical coordinates? Well, all I'm going to do is I'm going to substitute in what z, x, and y are in spherical coordinates. Z is rho cosine phi, x is rho sine phi cosine theta, and y is rho sine phi sine theta. You're going to square each of them. Okay, and we can factor out a rho squared sine squared phi from both of these terms here, right? And then I'll have under the square root, I'm going to have rho squared sine squared phi times cosine squared theta plus sine squared theta, which of course that equals 1. So rho cosine phi will then equal the square root, positive square root of rho sine phi. And you know, if I, you know, I have that, let me just make a note here. So rho, let me give myself a little more room. I have to train myself to give myself enough room. Okay, so rho cosine phi equals rho sine phi. And if I divide both sides by cosine of phi, and that's assuming the cosine of phi, you know, we don't let phi equal 0, right? But we can still get our picture. That'll be fine. It'll work. So then you get 1 equals the tangent of phi, right? You get, because these go away. We'll just say phi is greater than 0, right? So you get 1 equals the tan, I'm actually going to divide also by rho, right? I'm going to divide both sides. So what I'm doing is I'm taking this equation here, rho cosine phi equals rho sine of phi, and I'm dividing both sides by rho cosine phi. On the left then, I'll get the tangent of phi, and on the right, I'll get 1. Well, when is the tangent of phi equal to 1? When phi equals pi over 4. Remember, phi has to be between 0 and pi, right? That's the restriction on phi. Phi is measured from the positive z-axis. Okay, so if I put in, like, you know, the positive z-axis, there it is, right? Positive z-axis. All right, so the cone is here, right? This is the cone. All these points here, okay, all those points here are on the cone. The cone doesn't include inside the cone, it's the boundary, right? Well, every one of those points, phi equals pi over 4. So the equation of the cone is represented as phi equals pi over 4. Okay, so rho here, in terms of are there any questions so far? Rho is measured from the origin to all the points on the inside the solid. So rho can take on, right? Rho can take on these, maybe I'll put it in black, different values. So I'm just drawing an example, right? I mean, rho can, like if I were to draw this line segment here, protruding from the origin, going out to the sphere, stopping at the sphere, every point is going to have a row that ranges between what values, or what does rho range between? What's rho right here at the origin? What's rho equal to there? If you have a point at the origin, rho equals 0. That's right, Ellie. What about on the sphere? What's rho equal to there? Any point on the sphere, rho is equal to what? Well, how about this? Rho equals cosine phi for any point. Well, I mean, for this little line segment I drew, of course, phi would have a certain value. But what I'm trying to say is the points, we're trying to determine the limits. We're trying to determine the limits here. The limits for our triple integral. Okay, and what I'm saying is rho will go between, I want to be a little careful here. Rho will be greater than 0 and less than, I got to be a little careful here. Yeah, less than cosine of phi. Right, for any point in this solid, the rho is going to be between 0 and cosine phi. Now, what about phi? What's phi going to be between? Any point in the solid would have good a phi between 0 and pi over 4. Okay, are there any questions on that? I mean, the phi, right? Phi is measured from the positive z-axis. That's how phi is measured. Well, phi, like what would the value of phi be right here for points right here? What's the value of phi for that big blue point that I'm highlighting? What's the value of phi? Zero. Good, Charles. What's the value of phi for this point right here, this point that I'm highlighting? What would it be? Pi over 4. There you go. Good. Good, Charles. Now, what about theta? What about theta? What's theta going to be between? We have a whole like thing here, a whole solid 2 pi over 4. Theta goes from 0 to 2 pi. Sorry, theta goes from 0 to 2 pi. Are there any questions on those limits before I move to the next page? Please let me know. Malik, how are you feeling with that? Are you okay? Okay, good, good. Juliana, how about you? Are you all right with that? Very good, very good. And Emma, how about you? Are you all right with that? Okay. Well, then let's move on. Let's do our triple integral. Here we go. Here we go. So remember, I'm finding the volume. I'm finding the volume. So anytime you find the volume, your integrand, well, I got to be a little careful here. You're going to have a 1 here anytime you're finding the volume of a solid. dV is rho squared sine phi d rho d phi d theta. And then, okay, here are the limits. Rho goes from 0 to cosine of phi. Phi goes from 0 to pi over 4. Okay. And theta goes from 0 to 2 pi. So half the battle in these problems from sections 12.7 and 12.8 is finding your correct limits. But once you've found them, you know, and you've decided what the easiest coordinate system to integrate with, then you'll be good. Again, here I go. I iterate my integral. I'm gonna integrate with respect to r first. Okay, so sine of phi is a constant, treated like a constant in the inner integral. So sine of phi is treated like a constant. So the antiderivative is rho cubed over 3 times sine of phi. And then I'm going to substitute in cosine of phi and 0. And that's going to get me down here. You have the tools to do this triple integral. You have the tools. Let me give you a moment to catch up. Okay, so for now here, this inner integral, I mean, you want to look at this like a calculus 1 problem. You're doing one integral at a time. So one integral, well, what I mean is you want to look at this like a calculus 2 problem. You would know for sure that inner integral, you would let u equals cosine phi, right? All right, so you don't look at the whole like triple integral at once. You break it up and do each integral separately, right? Now, naturally, if you let u equals cosine of phi here, if you do that, then your phi limits are going to change to u limits. So root 2 over 2 comes because you have the cosine of pi over 4. That's square root of 2 over 2. And 1 comes from the cosine of 0. Right? So you made a substitution, your limits now are u limits. And this gets us down here. Are there any questions before I, well, are there any questions? Okay, Juliana's good, Madeline's good. Ian, how are you doing? You feeling all right with this? Okay, how about you, Gordon? For the most part, all right, good. Okay. Yeah. Well, Gordon, I took a class that was 6 hours long. So, you know, I know how you feel, but, uh, but that's okay. That's okay. Um, I mean, I had breaks and all that, but it's pretty. I said, man, I know the 6 hour class was broken up into 2 3 hour classes, so I know, I know. All right, may I go to the next page? Marwan, how are you doing? Are you okay with this? Okay, good. Well, all right, we got a double integral. So now it's like a chapter, like you learned double integrals earlier in chapter 12. So you just keep working it out. Now this, we could keep the one is greater than root 2 over 2, and we could have an integral where our bottom limit's mathematically, greater than our top limit. But generally, students are a little uncomfortable with that. So you notice I have a negative here, right? I have a negative sign, -1. So I'll absorb the negative, and then that causes these limits to switch. And then it's just a matter of computing it out. And web assigned likes exact answers. Okay, it likes exact answers. So so you're just going to keep working it out, and you will get. Turns out you will get pi over 8. That will be the volume of that ice cream cone. So I always think in terms of economics. I mean, if that were an ice cream cone, and how much ice cream's in the ice cream cone, and it's, I don't know, pi over 8, I don't know, cubic inches, whatever. But the point is, it's important to know. I mean, it's the best thing is to know the exact volume of the ice cream in the ice cream cone, because that then you'll know, you can figure out exactly how much money it takes to make that ice cream cone. And a lot of times, like in the food business, how many have heard that the margins are pretty tight? Sometimes these products, they might only be making like a dime or something. I mean, I don't think it's true for ice cream, but you know what I mean. How many have heard that sometimes the margins are pretty tight on food, for some things, in terms of profit for the store? Like the grocery store. Has anybody ever heard that? Oh, okay, Ian. Well, all right. The point is, if we can be exact, that's the best. I got you, Ian. Well, now you don't have to dip your ice cream in the water, right? In the tub to figure out the volume. You can use your multivariable calculus knowledge now. So, Ian, I think you'll like your ice cream better now, right? All right. Okay, so we have, you know, now this, again, this is a problem that we can verify this answer in MATLAB. So let's say, you know, you're doing your homework or you're on the exam, you get an answer like this and you want to verify it. You want to just verify it. You can do it in MATLAB. Let me show you how to do that. Is everybody done copying here? Maybe give me a thumbs up if you're ready to move forward here. Okay, excellent, excellent. All right, let me bring up the Blackboard again. Okay, so back into the MATLAB programs. Click here, and then section 12.8, there's a MATLAB program that will help you do a triple integral using spherical coordinates. Now, I don't have one there for cylindrical coordinates, but obviously, you know, you can do that. You can figure that out. So, but let's look at this problem that we just did in the MATLAB with this program. Click on that link there to get the MATLAB program to be brought up. Section 12.8. And here is the code. So here again, the clear vars command on the second line. My symbolic variables are rho, phi, and theta. My function is rho squared times sine of phi. That's my integrand. Okay. And again, I'm going to integrate with respect to rho first. So that's why, hold on here. That's why I have the rho there. Okay, the limits on rho are 0 and cosine phi. And now the second integral is with respect to phi. So therefore, phi, and the limits are 0 and pi over 4. And then finally, you got the theta as your final one, final variable. And theta goes from 0 to 2 pi. See how that works? So it's no different than the example we did with rectangular coordinates, the triple integral with rectangular coordinates. It's just we're using spherical coordinates here. Okay, well, let's see if we get pi over 8. I'm going to copy this. And I'll give myself a little space here. Paste it in the command line. Okay, I got it for the whole. It's just the way I have my view. But there it is. I'll hit enter. Oh, wow, look at that. Pi over 8. How many think that's pretty cool? How many are going to be using MATLAB to help them confirm answers? Okay, a lot of you. Good. Pretty much all of you, really. Okay. All right. On that, if there are no, are there any questions? Okay, I'll stop the recording.